Hi, and welcome to part 5 of this lecture. In this part, we're going to talk more about flip-flops. Up till now, we've only discussed the SR, master slave, and the D flip-flop. So in this part, we're going to talk about the JK and the T flip-flop. We're going to talk about their behavior and their implementation very briefly. We also need to introduce some new tables and equations. These are the basic descriptors that help us to understand these flip-flops. These are called the characteristic tables, characteristic equations, and the excitation tables. For the actual use, I suggest you read the supplement, which is called Design and Analysis Using JK and T Flip-Flops, and that goes into more detail about the actual use. There's also a few videos that have been put up to help you analyze these flip-flops in a little bit more detail. So first of all, the JK flip-flop, its behavior is very much the same as the SR flip-flop we've looked at before, where the J is analogous to the S, and the K is analogous to the R. So if you remember JK and you remember SR, then you can remember it as J equaling S and K equaling R. The one big difference is that where in the SR flip-flop, we weren't allowed to have S and R both equaling 1 at the same time. In the JK flip-flop, J and K both equaling 1 is allowed. In this case, when J and K are both equaling 1, then the flip-flop changes to the opposite state. We'll call this toggling to the opposite state. So if Qn was equal to 1, then Qn plus 1 is equal to 0. Since it's a master-slave flip-flop, it still has this ones catching behavior that the SR flip-flop had. Also, a note of caution that if the master changes to the wrong state, that the state will be then passed to the slave. So if we have the master falsely setting J equaling 1 and K equaling 1, then we can't reset it during this current clock cycle. We have to wait for the next clock cycle. In terms of the implementation, we have this symbol. In order to avoid the ones catching behavior, we can use a solution that uses a D flip-flop as the core of the flip-flop, and this will avoid that ones catching behavior. For the T flip-flop, it only has a single input T, and for T equaling 0, there's no change of state. For T equaling 1, it changes to the opposite state. So maybe you could think about it like a T flip-flop is a toggle flip-flop. When T is equal to 1, then it will toggle the flip-flop to hold the opposite state. So it's basically the same as the JK flip-flop, except where J and K both equaling to T. As a master-slave flip-flop, it still has the ones catching behavior, the same as the JK flip-flop had that behavior. And one thing important about the T flip-flop to remember is that it cannot be initialized to a known state using the T input. So we really need this reset in order to reset the flip-flop to a known state. Since it's only toggling, it doesn't matter what input we put into the T, we can't actually make sure that it goes to a specific state. So that's why we need the reset. Here's some notes about the implementation of the T flip-flop. The symbol looks very similar to the D flip-flop, except that there's a T there. And we can avoid the ones catching behavior by using an edge trigger D as the core of the flip-flop. So the basic flip-flop descriptors, we need to introduce a few new tools, 2 of which we use in the analysis and 1 of which we use in the design. So for the analysis, we need a characteristic table. And I'm just reading from the slide here, but it defines the next state of the flip-flop in terms of the flip-flop input and the current state. And there's a characteristic equation, which defines the next state of the flip-flop as a Boolean function of the flip-flop inputs and the current state. And we can also use the excitation table as a tool for our design, which defines the flip-flop input variable values as functions of the current state and the next state. The use of these specific to the JK flip-flop is done well in a video which will be linked online. In terms of the D flip-flop descriptors, so we have studied D flip-flops before. The characteristic equation is that the Q at time t plus 1 is equal to the input D, and the excitation table says that where we know what the next state is, we can work out what the D value input was. In this case, it's basically the characteristic table flipped around, but useful for design, whereas the characteristic table is useful for the analysis. This is the T flip-flop descriptors. The characteristic table says that when the input T is 0, then Qt plus 1 is equal to Q at T, so therefore there's no change. Whilst when T is equal to 1, then Q at T plus 1 is equal to Q complement. So whatever it was before, it's the complement of that. The characteristic equation is that the next Q is equal to T XOR Q. So remembering the truth table for XOR gate, when both T and Q are 0, then the output is 0. When either T or Q is 1, then the output is going to be 1, and when they're both 1, then it's 0. So if t is 0 and q is 1, then it stays at 1. If t is 1 and q is 0, then it toggles to 1. And if they're both 1, then q t plus 1 changes to 0. So the excitation table says that when we know q at t plus 1, then we can work out what t is. First one being no change, the second one being the complement. For the SR flip-flop, it's also one that we've studied in a previous lecture. The characteristic table is that both S and R being 0 keeps the next Q, as in Q at t plus 1, equaling to Q at t, so there's no change. When S is 0, R is 1, then the operation is reset, so Qt plus 1 goes to 0. When t is 1 and R is 0, then Qt plus 1 is set to 1, and when they're both 1, then the operation is undefined. So we make sure that both S and R are not equal to 1 at the same time. That's what this equation in the characteristic equation means as a second part. In general, Q at t plus 1 is equal to either S or complement of R and Q, making sure that both S and R are not equal to 1 at the same time. The excitation table shows that Q at t was 0, Q at t plus 1 is still 0, then the S was 0, and it doesn't really matter what the R is, so we have a don't care condition there. That's why we write the X. If Q at t is 0 and the next state is 1, it means that S was 1 but R was 0. It means we've set it. If Q was 1 and it changes to 0, it means set is 0 and reset is 1. And if both Q at t and Q at t plus 1 are equal to 1, then it doesn't matter what the set was, but the reset was definitely 0. Since we just stay, there's no change. For the JK flip-flop, basically the same as the SR flip-flop as we've already discussed briefly, apart from this extra allowance here where J and K can both be 1 at the same time, and that leads to Q at t plus 1 equaling to Q at t complemented, and we give the operation complemented, where previously for the SR flip-flop this was undefined and Q at t plus 1 was unknown. The characteristic equation doesn't have the extra stipulation that S and R can't both be 1 and Q at t plus 1 is equal to J and the complement of Q, or the complement of K and Q. The excitation table says that if Q at t and Q at t plus 1 are both 0, it means that J has been 0, and it doesn't matter what K was, there's no change. If it went from 0 to 1, that means J is 1, and it also means we don't care what K was because we know that J was 1. Whether K is equal to 1 or 0, it's still going to change from 0 to 1. When we have it changing from 1 to 0, it means that K is 1. It doesn't matter what J is. J could have been 0 or 1, and we would still have that behavior. And when Q was equal to 1 at time t, and it's still equal to 1 at time t plus 1, then it means K is equal to 0, and it doesn't matter what J was. There's simply no change. Here is an overview of the 4 flip-flops that we've looked at so far. The SR, the JK, the D, and the T. There's the symbols for each of them, the characteristic tables from each of them, the characteristic equations for each of them, and the excitations tables. This table came from Digital Systems Tutorial at University of Sydney. There's the web page there. They use slightly different terminology to us. They're calling it Q at the next state. It basically means Q at time t plus 1. Okay, now we're going to do an example of the flip-flop behavior given a clock and an input for both D or T. So I've got 2 flip-flops down here, a D flip-flop and a T flip-flop. I'm going to use the characteristic tables to find out what the output waveforms are for the flip-flops shown. So remembering for both of these, things happen on the rising edge of the clock, that is here, and also where the lines are. So at first, we'll assume that they're both 0. Just write 0 and 1 and 1 and 0. Then after some small delay after the rising edge of the clock, we have the D flip-flop changing the Q to whatever the input D is. So that goes from 0 to 1, stays at 1. And for T, it toggles it. So it was at 0, so it changes to 1. And that continues along until the next rising edge, and we have D equaling to 0. So this changes from 1 to 0, and at this point T is equal to 0, so there's no change, we just continue on. At this next rising edge, we have D equaling to 1, therefore QD changes from 0 to 1, and T toggles from 1 to 0. And that continues along until the next rising edge for both of them. And then at this point, we've got D now at 0. So QD goes from 1 to 0. And QT, since it's 0, means it doesn't toggle. It just continues along at 0. And that's good. That's the right answer. For the next one, we've got an SR and a JK flip-flop. Once again, we're going to use the characteristic tables that we developed to find out the output waveforms given these inputs here. So the S, remember, equaling to the J or equivalent to the J, and the R equivalent to the K. So we've got, for the first one, the input S having this waveform, and for the second one, it's the input J that's connected to this. And then the R and the K is connected to the R and the K. And then the top one is the clock, of course. So at first, they're both starting at 0, and then a little bit past the line, things are changing on the rising edge again. We have S equaling to 1. Therefore, the SR flip-flop is set. For the JK, it's also set. And this continues along until the next clock pulse, at which point we've got set equaling 0 and reset equaling 1. So that means they're both changed from 1 to 0, and that continues on. Now here is the point of difference. That is where S is equal to 1 and R is equal to 1, or J and K are both equal to 1. So for the SR, this is undefined. We don't know. It could be 0, it could be 1. So we're going to write it like this with a question mark, because we don't know if it's 0 or it's 1. For the JK flip-flop case, then we simply know it toggles. So it was 0, goes to 1. So it goes like this. At the next clock pulse, we have set equaling to 0 and reset equaling to 1. So therefore, it definitely goes either from 0 to 0 or from 1 to 0. So we know that converges upon 0. And for this case, when set is 0 and reset is 1, it also changes to 0. So that's okay. That matches the answer. So that's good. And this ends this part and this lecture. Since the details on these flip-flops was presented rather rapidly, I suggest you read the supplementary reading material on the design and analysis using JK and T flip-flops. Also watch the other videos which are suggested. In the next lecture, we're going to be talking about registers. So see you then.